Navier-Stokes-Vlasov-Fokker-Planck equations.
Thank you for the introduction. And first of all, I would like to appreciate all the organizers for giving me a chance to speak in this nice conference. And today I would like to talk about some Navier-Stokes-Vlasov-Fokker-Planck equations. And in the last session, Dr. Terasa talked about some coupled system with the Navier-Stokes equations, and actually non-Newtonian Navier-Stokes equations and some Cahn-Hilbert equations. And this is some equations describing some interaction between fluid and particle. And this is a joint work with Myung-Ju Choi in Hanyang University and Byung-Keun Kang in Yonsei University. And first, I would like to this model is, I would like to introduce some physical meaning of these models, and also I would like to consider some incompressible Navier-Stokes equations coupled with Vlasov-Fokker-Planck equations. And then I would like to speak about some compressible Navier-Stokes equations coupled with Vlasov-Fokker-Planck equations. And we will consider 2 and 3-dimensional case, and also some, in 2-dimensional case, we consider some global existence of strong solutions with large data. And also we consider some, in the 3-dimensional case, we will consider some global existence of the strong solutions near the equilibrium. And first, I would like to speak about some physical meanings. And first, we would like to describe some interactions of fluids and particles. If we consider some aerosols, and then if we spread out some particles into the air, then actually the spreaded particles does not affect the motion of the fluid, the motion of the air. But the motion of the fluid, the motion of the particles will be affected by the motion of fluid. And this is the interactions of fluid particles, and there are some examples, aerosol and spray. And also, there are some applications, these fluid particle interactions, for example, there is some applications in biotechnologies, and wastewater recycling, and diesel engines, and etc. So in this setting, we will describe the motion of the fluid by the Navier-Stokes equation or compressible Navier-Stokes equation, some kind of, and in some cases, Euler equations. So the governing equations is constituted of some fluid equations and combination of fluid equations and Fokker-Planck or Vlasov equations. Also, there are some two regimes, some flowing regimes and bubbling regime. And actually, we will just consider just flowing regimes. And so, let me first think about some derivation of the equations. And this is done by Caflisch and Papanicolaou in 1983. And if we consider, at first we consider two fluid models, and there are one fluid here, and there is also another fluid is here. So this is, and we will state there are two fluids, U sub P and U sub F. And U sub P is the average velocities of the actually fluid, some fluid, and another fluid U sub F. And also phi is the volume fraction density of the particles. So then volume fraction of one fluid. And then, and Caflisch and Papanicolaou considered, then UP, the equation of UP can be replaced by some kinetic equations, for example, Vlasov equations or Vlasov-Fokker-Planck equations. And so then, so we have, basically we have some Navier-Stokes equations. This is Euler equations. There is some drag force here. Navier-Stokes equations, and there is some drag force. Drag force can be described by some difference between two velocities. And so basically we have these kind of various combinations, and we can choose for the fluid equations, we can choose compressible Navier-Stokes equations or compressible Euler equations, or incompressible Navier-Stokes equations or incompressible Euler equations. Also, we have some variations for the equations describing the particles, the motion of particles. We can choose Vlasov equations or Fokker-Planck equations. And then, so also there are many situations, and if we consider, I would like to say about classifications of sprays. This is done by Oruke in 1981, and in his thesis, he classified the equations. He considered as a fluid equation, he considered compressible Euler equations, and for describing the particle equations, the kinetic equations, he chose the Vlasov equations. And at first, if we consider very thin spray models, so just the particles are very thin, so the fluid motions will not be affected by the particle motions. So there is this is a kind of independent equations. It is not affected by the particle motions, but particle motion is affected by the fluid motions. There are drag force. This V is the velocity of the particles, and U is the velocity of the fluid, and then F is some distribution functions. Actually the probability density functions, and then we have this kind of Vlasov equations, and we consider compressible equations. This is the very thin case. And next is if we consider some thin spray models, comparing with the previous case, the fluid motion is also affected by the particle motions. There are also some drag force here. Capital F, we have the same capital F here, and so we have some compressible Euler equations, but there is some, as an external force, we have there are effects by the particle motions. I would like to mention that some P is the pressure of the law. And next, if we consider moderately thick, and the previous one is the thin spray models. If we consider moderately thick spray models, and for almost the same equations as before, but this is the thicker than previous one, then the particles can collide each other. So there is some collision corners, and there are some, if we consider collision corners, so we have this kind of equations. And so if we consider thicker and thicker spray models, then actually the equations is much more complex going to be. And this is a thick spray models. If we consider compressible Euler and Vlasov. Comparing with the previous cases, in the previous cases we ignore the volume fraction of the particles, but it is now the particles are much thicker than previous one, then we cannot ignore the volume fractions of the particles. So we have the volume fractions here. Then the volume fractions, there is some evolution of the volume fractions. And so we have still collision term, and fluid motion is affected by this one. And so we have the much more complex equations. And usually we will consider, okay, at first, and we just consider the case thin spray models, and incompressible, we don't consider about the collision term of the particles or volume fraction. We will ignore that, and just we will consider thin spray models, and then and also we will choose in this case we will choose the incompressible Navier-Stokes equations as our fluid equations and Vlasov-Fokker-Planck equations as our kinetic equations. And we have, so there is some Fokker-Planck equation. This is the Fokker-Planck term, and we will consider sigma is greater than 0. And if sigma is 0, then we will say this is just the Vlasov equations. And also we have some direct forces here. And this is so capital F is there is some, and there is a effect of there is some, this term has some u inside of it. And also we will consider macroscopic, we will choose macroscopic fluid equations. And so u satisfies, in this case we will choose the incompressible Navier-Stokes equation as a fluid equations. And also there is some direct forces here. And we will choose the special direct force, just the linear direct force. And friction force is proportional to the relative velocity, and u is the fluid velocity and v is the velocity of the particles. So we will choose these linear properties, this linear friction force. And then if we substitute capital F, small f, by this one, then we set f sub 0 is just constant, so we will choose f sub 0 is just 1. And if we choose the old constant, for example, the viscosity and the sigma is just 1. If we choose all the constants are to be 1, then we have these kind of equations. So f is if we consider 3 dimensions, then f is some probability density functions with respect to time and space and velocity of the particles and v phase space. And so we have this kind of equations. And then for these equations, I would like to mention some history of the other mathematical studies. And in 1998, Hamdashi constructed of the weak solutions to the Vlasov-Stokes system in a bounded domain, and we are with specular reflection boundary conditions. And also Baudin and Deblay and Grandmont Moussa in 2008, they constructed some global weak solutions for the 3D incompressible Navier-Stokes-Vlasov equations in a torus. And also actually using the same way, we can construct the global weak solutions for the 3-dimensional incompressible Navier-Stokes-Vlasov-Fokker-Planck equations. And also in 2007, and Mellon and Basser constructed the existence, they proved the existence of global weak solutions for the compressible Navier-Stokes-Vlasov-Fokker-Planck equations in a bounded domain with Dirichlet or reflection boundary conditions. And in 2006, Baranger and Debele obtained the local instance of the compressible Vlasov-Euler equations. And also, Gudong, Ham, Musa, Zhang in 2008, they obtained some stability of solutions near Maxwellian. And if we consider some steady solutions, then we have this kind of steady solution. This is we will call this a Maxwellian, and in three-dimensional torus. And they obtained the initial data is just small perturbations, then they can obtain the global instance of strong solutions. And also 2010, and have proved some perturbation of the steady state of the system is globally stable for arbitrary initial data. And also Gudong and Jabing and Basser in 2004, they considered some hydrodynamic limit of the global weak solutions. And also 2010, and Carlo, Duan, Musa considered global existence of classical solutions close to the equilibrium to the three-dimensional Vlasov-Euler-Fokker-Planck equations. And at first, we will consider we will consider the incompressible Navier-Stokes-Vlasov-Fokker-Planck equations. In this case, if we assume the initial data satisfy, if we give some weight like this, and also f sub 0 is the initial data, and also we consider u sub 0 is satisfied this one, and k is greater than 3 minus 2 over p, then we obtained there exists f and u such that satisfying this one. So this is in two dimensions. In two dimensions, we have, if we consider some Navier-Stokes equations, then we have, for the Navier-Stokes equations, it is in two dimensions we can have some global existence of the strong solutions. And for the Vlasov-Fokker-Planck equations, actually if we consider in two dimensions, if we consider in any dimensions, actually if we ignore the u, then this is just a linear equations. Actually this is a linear equations, so we can have some good properties. And furthermore, we have some this kind of Fokker-Planck terms. But if we consider some higher regularity, so only the problem is that like this, there is a u and f, there is some this is coupled term, and we have some dissipation here for the u, but we don't have any dissipation for the f, any clear dissipation for the f for these terms. We just have the Fokker-Planck term, but it is dissipation with respect to v, not x. And so if we consider two good equations, and then for these two equations, and to prove the global instance, we will use some high moment estimates, and I will show later. And also we will use some Professor Donghoche's proof for the proof of the sorry, this is a typo. Proof of the classical solutions to the partial viscous Bush-kinetic systems. If we consider some two-dimensional Navier-Stokes equations and just the Bush-kinetic systems with no dissipations, and then if we have if we consider some coupled systems, then using the Bridges-Wiener inequalities, then we can have the global instance of the classical solutions. And actually our system has the similar structures. For the u, we have some, for the the U equations, we consider two-dimensional Navier-Stokes equations, and for the coupled systems, the coupled Vlasov-Fokker-Planck equations, we don't have any dissipations. And then, so let me consider some high moments. Actually, this is some a priori estimates. The first one is that this is some weight here. If we consider the initial data is bounded in some weighted LP space, and then K is satisfied this one, and then still we have the weight. Actually, we can have this kind of even in this kind of higher moment, then we have the conservations here. And actually this can be obtained by some a priori estimates. And for example, this is a well-known a priori estimates for the Vlasov-Fokker-Planck equations, and there is some initial data. Only using the initial data we can control all the other terms. And this is also another a priori estimates, and any LP norms can be controlled by the initial data and T. And for the estimates of the high moments norm of the app, we have just multiplying and integrating, then we have this kind of equations. Then only the problem is from here. This is the coupled term. We have U is here. So then let me consider J sub 11. J sub 11 can be controlled like this. Just we will use, this is integrable, and to make this term to be integrable, we have some restriction on the range of the K. And then we have this, just using the Helder inequality, then we have this one. And then using the Young's inequality, just using the Young's inequality, then we can control any other terms can be controlled by the regularity of the weak solutions, and then all the other terms can be controlled by using the Groner's lemma. And next, let me consider some global instance of the strong solutions. And if we consider just Vorticity equations, omega is the curl in 2 dimensions, and n is the integration of the app with respect to v. And then we have, just using the a priori estimates, then we have, if we have just multiplying and integrations, then we have this one. And the most typical term is here. This is the coupled terms coupled with U and F. And so this is just a V, and this is phase space. Then we can estimate this one by the high moments estimates. And also this one, J, and we will consider J sub 23. Then this term can be controlled by this kind of Bredges-Weinger inequalities, and we will estimate this one by L infinity, and then other terms this is by LP, and this one is by LP, and this one by LP over P minus 1, and this L infinity norm can be controlled by this one. And then if we consider the energy estimates and these log terms, then if we use the Groner's lemma again, then we can control every terms. And actually, this is the whole domain, and previous things, the existence, global existence of the weak solutions is obtained in boundary domain. So but using the similar ideas, in the standard method, then we can prove the global existence of the weak solutions in this space, because we need to prove the global existence of strong solutions. We need the energy estimates. So to justify this kind of energy estimates, we need this kind of some proportions. And also for the higher regularities, we will use this kind of notations. This alpha is the derivative with respect to x, and beta is the derivative, the multi-index, the derivative with respect to v. Then we have this kind of notations. Then this is some weighted norms, and then we can have higher regularities. And if initial data is good, then we can show for the 2 dimensions, for any capital T, we can show the global existence of f and u, and f and u satisfies this kind of some higher regularities. And also, next, let me consider the compressible Navier-Stokes-Vlasov-Fokker-Planck equations. And we will consider this is a compressible Navier-Stokes equations, and we have some drag force here, and also Vlasov-Fokker-Planck equations, and we have drag force. And in this case, we will consider for the 3-dimensional case, we will consider the spatial domain is just the 3-dimensional torus. And then let me consider steady state solutions for these equations. Then rho is just rho star, and we have, and capital F, the steady solutions is like this. The normal distributions, the probability density functions. And we will call this is Maxwellian. And then for the simplicity set, rho star is just 1, and also set sigma is just rho minus 1. And let me say F is mu plus square root of mu F. And then this, from using this kind of notation, small f and sigma, then we can rewrite the equation 7 into this one, 8. And so we have incompressible Navier-Stokes equations, and we will set all the viscosity is just 1, all the constants is 1, and then we have, and also we just consider, we will only consider the case, the isotropic fluid, isotropic case. And then we have this kind of equations like this. And then for this case, we can consider the near equilibriums. If we consider if the initial data is very small for the previous equations, then we can show the global distance of the classical solutions to these equations. And also we can have, in 3-dimensional torus, we can have exponential convergence. So actually this is some notations. This is just the L2 inner product with respect to X and V, and this is a L2 inner product with respect to V, and also this is some notations, multi-index notations for the partial alpha beta, and also we can define some norm like this, and also this is some linearized Fokker-Planck operator. And this operator is non-negative. If we consider LFFV, then we have this one. So, in the previous one, we have this operator here. So this is in some sense, this one is almost same as the, how to say this. If we use this is almost distributions, almost same as the Laplace V, but there is some difference. I would like to show the next lemma. Let me say L is the operator, this one, and then we have, and we can have this is some kind of standard lemma for the Fokker-Planck operators. If L0 is 0, then the corner is the constant multiple of square root of mu, and so we can have this one, and then there is some constant c and I minus p sub 0 z and sigma, and g is let me consider the p sub 0. P sub 0 is the projection operators, and L2 to the n is the space spanned by square root of mu, and so this is almost same as almost cursive, but there is we should compensate this one to obtain some exponential decay. And let me introduce some a priori estimates to obtain existence. If we consider some small data, and then we would like to obtain some global existence of the solutions, small perturbation of the equilibriums, and then actually this is some standard a priori estimates, and if we consider some torus, to compensate we need some mean value of the integration of the rho u, and then we have this kind of a priori estimates, and there is other terms I sub 1 and I sub 10, and all these terms can be estimated by the standard methods, just Helder inequality and Young's inequality, like that. And for the other a priori estimates, if we consider these equations, we have two. For the a priori estimates, we have these two, and if we consider these three. And if we add these things, in the previous one, in the left-hand side, we have this one. So to obtain this one, if we add these three things, then we have some good ones. And if we add these three things, then we have this one. And also, then if the supremum of this one is small, then we have this one. And so we need to obtain decay estimates, we should compensate the missing dissipations. So for the dissipation of L, and then if we consider this, if we have this kind of lemma, then we have exponential decay, and so to compensate the missing dissipations, if we consider Kawashima compensating functions, and this is a standard actually initially this is Kawashima compensated functions was initiated by Kawashima, Professor Kawashima in Kyushu University, and also the Fokker-Planck case, it has been studied by Tongyang and other mathematicians, and using their Kawashima compensating functions, we just consider some Fourier series. Then we have some Fourier series. This one is this W1 is just will be recover the previous. This is W1 is the nth coefficient of the Fourier series of the square root of mu, and so we can recover the missing dissipations here, and then for this case, there is some other things, but this one can be controlled by the previous lemmas, and also only the missing dissipation is here, and then we can control the missing dissipations. Then we can have the exponential decay, and this is the end of proof. And thanks for your attention. Thank you.